Let me start off by saying that I'm not an artist, so this is what most of the drawings are going to look like. If you don't like the way this looks right now, instead of complaining, please move your mouse cursor over the back button on your browser and press the mouse button. You won't regret it. Having said that, this video is going to be all about protecting and controlling motors and relays. Now let me start off by saying you can't just hook a motor up directly to a microcontroller's output pin. If you did that, you'd just break the microcontroller. This is because most microcontrollers can't source or sink a lot of current. Usually the limit is something like 30 milliamps, or possibly less than that. What we need is something that can amplify a signal, like for example, a transistor. Take a 1K resistor and put it in series between the microcontroller and the base of the transistor. Then connect the motor as you see on the video here. But there's one more important thing you need before the circuit will work. The motor's an inductive load. But what does that mean for our circuit? When you turn off an inductive load, the induction of the load tries to keep the current going, but since it has nowhere to go, it causes a voltage spike, which is likely to destroy the transistor. But the solution is quite simple. Simply put a diode in reverse parallel, like that, across the motor terminals, and your circuit will work fine, assuming you've chosen the right transistor. Let's go over that next. Let's use the specifications of this motor for our demonstration. You might think that this transistor would work because it has a current capacity of 1 amp. Whoa there, Turbo. There's another rating you've got to pay attention to as well. That's the wattage rating, or power dissipation. Now how do you get the wattage? That's simple. It's volts times amps. 600 milliamps is the same as 0.6 amps. 0.6 amps times 5 volts equals 3 watts. Oops, we just destroyed a transistor. Clearly we need something more beefy than a small signal transistor. Now, if we're just switching the motor on and off, we could use a relay. A relay is a device that has an electromagnetic coil pointed at a set of electrical contacts. When the coil is turned on, the contacts move and either open or close depending on the type of relay. Let's take the specs of a real relay for comparison purposes. This one has a contact rating of 10 amps at 400 volts AC. That's more than enough for what we need. We're talking about 600 milliamps at 5 volts DC. But controlling this with a microcontroller would still require a transistor because the relay itself draws 71.4 milliamps, which is probably over the rating of most microcontrollers' output pins. Thankfully, using a transistor to control a relay is quite simple. Just check this circuit out here. You just put a 1K resistor in series with the base to limit the current, and just wire everything up like you see here. It's an NPN transistor, so you'll want to put it on the low side, that is, sinking current. Also, notice that there's a diode across the relay in reverse parallel. Well, this is because the relay is an electromagnetic coil, which by definition is an inductive load. I already explained about diodes and inductive loads with transistors, so I don't think I need to explain it again. So this circuit should work fine for simply turning a motor on and off. But there are some disadvantages to using relays instead of transistors, or in conjunction with them like you see here. Relays are slower than transistors, they're noisy because they have moving parts, they don't last as long as transistors, again because they have moving parts, and they're larger than most transistors. The first thing that you can do with a transistor directly controlling a motor that you can't do with a relay is control its speed electronically. But first, let's figure out how to find the correct transistor to control the motor directly. Here's a transistor that's a bit bigger, both physically and in the amount of power it can handle. Let's look at the wattage. Power max is 30 watts. Impressive as that may sound, it can't do that on its own. That may sound like false advertising, but it's actually common. This transistor has a metal tab with a hole in it, on which you can mount a heatsink. The heatsink will help dissipate the heat, hence the term heat sink. But how do you find the right heatsink for this transistor? Well, it's not that hard to do actually. One of the specs of a heatsink is package cooled. So that means that's the type of transistor package or body that this heatsink is designed to mount to. So let's figure that out by going to the spec sheet again. If you see here, it says package/case is TO220. Do a quick search on DigiKey and you'll find this heatsink. Now all you need is a few screws and washers and such to mount the heatsink to the transistor, and you're golden, baby. Alright, now let's talk about PWM, or pulse width modulation. Basically, PWM is when you turn the motor on and off very rapidly. The thing that changes the speed of the motor is the duty cycle, or on time versus off time. An 80% duty cycle would mean that it's on 80% of the time. A 20% duty cycle would mean that it's on 20% of the time. The lower the duty cycle, the slower the motor will go. If coded properly, the switching will occur quickly enough that the momentum of the motor will keep it running at a relatively constant speed depending on the duty cycle. The higher the duty cycle, the faster the motor will go. In some cases, you might hear a buzz or a whine or a hum from the motor due to the frequency of the switching. However, if the frequency is high enough, you won't hear it. Don't ask me how to code a PWM system because I don't know. I've never coded one before because the Arduino has that built in, and that's the only microcontroller I've ever used. Now let's go back to the motor's current requirements. This one draws 600 milliamps when stalled. A relay, or properly heat-sunk transistor, should be able to handle this indefinitely. Now I'll say that again. The relay, or the transistor, should be able to handle this indefinitely. That doesn't mean that the motor will, however. Now I keep talking about stalls and stall current, but what does a stall mean for an electric motor anyway? A stall is when the motor has a nominal voltage applied, however, the motor cannot turn for whatever reason. This could be for any number of reasons, like there's something blocking your mechanism from moving, lack of lubrication, or your robot's trying to drive into a wall. The bearings on your motor either need lubrication or they've failed. Now, if the bearings in your motor failed, then it's probably time for a new motor anyway. However, the other conditions I mentioned are probably reversible, assuming the motor survives the stall condition. But why is a prolonged stall condition bad for a motor anyway? In a nutshell, the windings aren't meant to be on all the time. This isn't a problem when the motor's spinning because each winding is on for just a fraction of a second. But if the motor stops spinning, then one of the windings will be constantly on, and that's no good. They'll just get really hot and eventually burn up. Another thing is that some motors have vent holes or even a fan attached to the rotor to keep the windings cool. But that fan being attached to the rotor will stop if the rotor stops, so that'll also cause things to heat up. Probably the best thing to protect a DC motor with would be a PTC. A PTC has low resistance at its nominal state, but if you try to draw too much current, the resistance goes up. A PTC rated at approximately half the motor's stall current rating should provide sufficient protection while still allowing it to start and run under load. If it doesn't, one rated at 75% might work, but it probably won't provide very good protection. If you want to reverse the direction of a motor with transistors, here's an example circuit. It doesn't have base drive resistors, but it does show the basic principles of something called an H-bridge. It's called an H-bridge because it looks like a big H. H-bridges are a bit more complicated, so I'll actually make a whole new video on that if anybody wants it. If anybody wants it, go ahead and leave a comment or personal message me on YouTube, and I'll tell you that I'm working on it. So, that's pretty much it for this video. Till next time, bye.